Hello everyone. In this video I'm going to talk about what we can do with a correlational regression, what we can do with a causal regression, and what are the assumptions that we need to go from correlation to causality. I'm again going to assume that you've already watched the video on regressions for correlation so that we're all on the same page. I discussed in that video that as long as we have a random sample, then our regression with our sample is going to consistently estimate the population parameters. What this does is it establishes a pattern of a relationship between x and y. This allows us to take a new value for x, plug those x's into the estimated equation, and make some prediction of what we think that y will be. This is what we call a passive prediction. Just saying that if we know x, we can make a pretty good guess of what y is going to be. What we cannot do is actually claim that a specific change in one of our explanatory variables is actually going to cause a change in the dependent variable. All we're saying is that this tends to be the relationship. We're not making any claim about why that is, or making any claim about causality. For example, if we go back to our estimated demand function that we've been working with, we could ask the question, what do I think the quantity demanded is going to be if the price is 100? We plug 100 into our equation and simply predict that the outcome is going to be a quantity of 3,327. We can make this claim while still acknowledging there might be other factors out there. It's just that when the price is 100, then on average, the quantity tends to be about 3,327 units. Let's think about a few different situations where we could apply this type of passive prediction into a business situation. One might be to build a personalized marketing strategy for an individual person. We see this online all the time when you get targeted ads based on what Google thinks that you might want to buy. This is based on your browsing history, your purchasing history, and so forth. There was also a famous example from a number of years ago where Target was able to predict whether or not a shopper was a pregnant woman based on what they were buying, and then they sent out ads for baby-related products based on that prediction. Google or Target does not actually care why it is that you want to buy this thing. They can't change who you are, but what they can do is decide that you are a likely candidate to want to buy a certain product. You could also use a passive prediction if you are a hiring manager. You could take a sample of your existing employees and say, what are the characteristics associated with people with high productivity? And you could hire people based on what you predict their productivity is going to be. It doesn't actually matter that you have precisely estimated a causal relationship here. You just care about who tends to be a good worker. In general, we can think about any situation where what we're interested in is the final outcome, but we don't actually have an ability to change X. Another example that I like to use is in a political campaign. If you're a campaign manager, you're interested in trying to encourage people to vote, but only if they are going to vote for your candidate. At the end of the day, it doesn't really matter what is causing them to vote for your candidate. You just want to know, are they pretty likely to do so? And if you see a neighborhood where there's a lot of people who look like your candidate's supporters, you might want to target your efforts to that area. We've already talked about the main limitation of passive prediction, that we cannot make any kind of causal claim. We also need to say that we can't extrapolate the results from a correlational regression beyond the scope of the population. So for example, if we have a regression predicting the amount of crime in communities in the United States, we can't use that to talk about predictions of crime in any other country. Likewise, if we have a sample of only men, we can't really make a claim about what women would do, and so on. Now that we've established what we can do and can't do with a regression for correlation, let's talk about causality. To run a correlational regression, we actually needed very few assumptions. We were just saying that there's a relationship in the population, we have a sample, we're going to try to estimate that relationship. For causality, it gets a little bit more complex because we're actually trying to estimate a data generating process that we are going to assume has a direct role in creating the data that we observe. We first talked about DGPs several videos ago, But just to remind you, a general form of the DGP looks like this. We have our dependent variable y on the left-hand side, and on the right-hand side we have two parts. We have a function of our x's, our explanatory variables, that's called the determining function, and then we have everything else, epsilon, our error term, which is everything else that has an impact on y that's not one of our given x1, x2, and so on. The first assumption that we have to make in order to interpret a regression causally is that our data generating process has to be linear in terms. That is basically saying that the determining function looks like a regression. We have our beta naught plus beta 1x1 plus beta 2x2 and so on. When we run a regression, we are imposing this type of relationship on the variable, so in order to actually estimate the DGP had actually better look like that. This is kind of a philosophical point because we never actually see the DGP, but this assumption is there in the background. If our DGP looked nothing like this, running a regression would estimate something, but it certainly wouldn't be what's going on in reality. Assumption number 2 is one of the most important things to talk about in all of regression analysis, and one that does not get talked about enough. Assumption number 2 states two things. First of all, the expectation of epsilon is 0. This means that in the population, the error term epsilon has a mean of 0. Sometimes it's positive, sometimes it's negative, but on average it is 0. It must also be that epsilon has 0 correlation with any of our independent variables. And we can write that as the expectation of epsilon times x1 is 0, the expectation of epsilon times x2 equals 0, and so on. This part is actually the more important of the two. And this is the assumption that we call exogeneity. Exogeneity implies that no unobservable factors exist that are correlated with both x and y. Remember that any unobservable factor correlated with y has some role in forming epsilon. And if any of those things are correlated with x, then the exogeneity assumption is broken. This is really, really important because if this assumption is broken, then we're going to have bias in our estimates. And that's going to make it impossible to make a causal claim about our regression. If we want to claim that when x goes up by 1, then y changes by beta 1, but our estimate of beta 1 is biased, then we can't say that anymore. What we mean by bias is a persistent error. That is to say that on average, our estimate is going to be off. And no matter how big our sample size is, and no matter how precise our estimates are, they're still on average going to be wrong. This problem is called endogeneity. Endogeneity is enemy number 1 in regression analysis. It's a very common problem and one that requires us to think carefully about before we make causal claims. We're going to talk about endogeneity more in a coming video. Before we move on, I want to talk about our demand example and think about whether or not our assumption of exogeneity is reasonable. Remember that our error term epsilon in this equation is influenced by all of the factors that are correlated with quantity demanded, but that are not already in the equation. Currently, we only have price in the equation, so there's all kinds of stuff that could potentially be in epsilon. What kind of things influence the demand function? We could have things like consumer income, things like the price of substitutes and complements, the population of the buyers, all kinds of things. The fact that we have some factors that are unobserved inside the epsilon by itself is not the problem. The problem is going to arise if any of these things are correlated with price, the variable that's actually in our regression. So if the price of x is, for example, correlated with the prices of its substitutes and complements, then our assumption is broken. And I think that in a lot of cases, that's probably true. They probably are correlated. Prices of goods tend to be correlated with each other. Price also might be correlated with income. In higher income places, prices tend to be higher. You can see that in this simple equation, we can make a clear argument that there is endogeneity here. We're going to put this issue on hold for the moment and come back to it later. For right now, I do want you to understand that this is a big problem, but for the moment, we are going to move on. If our two assumptions here are satisfied, that we have a linear DGP and no correlation between epsilon and x, then we have consistent estimates. That is to say that our beta hats will converge to our betas as the sample size increases. To do a hypothesis test with a causal regression, we go through the exact same steps as we did in the last video. Again, just remembering that we have to have all of our assumptions in place. The DGP is linear in terms, and we have an error term with a mean of 0 and no correlation with explanatory variables, in addition to our previous assumptions that we have a random sample and a large enough sample size to apply the central limit theorem. Since we already covered the specifics of hypothesis testing in the last video, I'm not going to do that again here. Let's talk about what we can do with a causal regression that we can't do with a correlational one. The main thing is that we can make what we call active predictions. Once we've established causality, we can do something very powerful. We can say, if we were to change x, this is going to be our predicted change in y. We're no longer tied to just saying that these variables tend to go together. We can say that when x changes, this is what's going to happen to y. As before, we can, of course, not extrapolate to populations that we did not sample. The causal interpretation is very useful because active predictions are usually what we're trying to do when we're trying to make a decision. In business, we might want to think about, well, what would happen if we were to change the price? How much would our sales change? Or maybe how much would sales change if we increased our advertising? These are questions that a correlational regression simply could not answer. From a government perspective, we might want to see how behavior of consumers would change if we were to change the tax rate. In general, what we can do with this is to predict how people will respond to any kind of policy change, whether that's a business policy or a government policy. I'm going to wrap up this set of videos by coming back to the concept of fit, as measured by r squared. Remember that r squared is a measure of how closely our estimated model from our regression fits the observed data. If the r squared is high, that means that we can fairly accurately predict values of y. I've mentioned before that r squared is relevant only in certain situations and not others. It's useful to frame these in our two concepts of passive and active prediction. If what you're trying to do is passive prediction, then what we're trying to do is accurately predict y based on given x's. A high r squared is important to this kind of regression. If the model is poorly fit, then that means we're missing a lot of the variation and we're not doing a very good job predicting what y is. Going back to our political campaign example, if you are not very sure who somebody's going to vote for, then you might be getting it wrong a lot of times if you're trying to encourage them to get out and vote. They might go and vote for the other candidate. However, if we are trying to do an active prediction, r squared and model fit don't matter. When we're making an active prediction, we want to know when x changes, how much is y going to change? The actual level of y doesn't really matter. What we need for active prediction is not fit, but estimate precision. In economics, we tend not to think too much about r squared because establishing causality is usually our goal. Remember that economics is all about decision making. And when we're trying to make a decision, we want to know how will people react to the decisions we make. And that's what an active prediction is all about. That brings us to the end of this set of videos. Our main goal here has been to distinguish between a correlational and causal interpretation of regression and the assumptions that we need to be in place to make those interpretations. Critically, we have also gone through the steps to conducting a hypothesis test on our regression estimates. If you have any questions about any of this, please let me know. Thanks for watching.